Good morning everyone, and welcome to today's worked exam answer video. Today I'm having a look at a question that covers some of the periodic trends of the elements in period 2, with a particular focus on first ionisation energies, successive ionisation energies, and then a little bit on second ionisation energies as well. Now, you will be expected to know the trends for period 3, and that comes up in both atomic structure and the periodicity topics from the AQA specification, but the trends across period 3, those are reflected across period 2 as well. So the question here is just trying to throw you a little bit by choosing period 2, but having a look at the periodic table, which I have here, the pattern in terms of having the 2 S block elements and then the gap and then the 2p elements is exactly the same as it would be in period 3. So we see the same trends across period 2 and period 3 in terms of atomic structure. In terms of atomic radius, which is the first trend that we have to discuss, and for ionisation energies as well. So there'll be the same general trend in first ionisation energies across period 2 and 3. There will also be anomalies in the same positions. So in period 3, you'd need to know that it's between magnesium and aluminium, that there's a dip for aluminium, which we wouldn't expect. That would be matched in period 2 by there being a dip for boron that we wouldn't expect. And then the other is between phosphorus and sulfur. In period 3, sulfur is less than phosphorus, which we wouldn't expect. That's also mirrored in period 2, with oxygen being less than nitrogen that we wouldn't expect. So if it talks about period 2, you are basically using your knowledge of period 3 and applying that to these particular elements. So I will have the periodic table out for this so that we can have a look at the positions of these elements, because I think that's going to be helpful, not least because we are thinking about period 2 elements, but we're only thinking about a certain number of them. So in the first question, we're only thinking about carbon to fluorine. Second question, we're then thinking about carbon to neon. And then in the last question, we're looking at the whole period from lithium to neon. So yeah, I'll have my periodic table here just so that we can refer to it as and when feels appropriate to do so. So part A says that we have to identify the period 2 element from carbon to fluorine, and that's so important because I've seen so many students over the years just pick any element from period 2 without picking one from the specified range. And we're looking for the one that has the largest atomic radius, and then we have to explain our answer. So the fact that it says identify the period 2 element means that we can either give the name or we can give the symbol. Don't have to do one or the other, and we are going to have to explain our answer. So the 3 marks here are going to come 1 for identifying the element and then 2 for our explanations. So we're only focusing on carbon to fluorine. So if I bring the periodic table back in here, carbon is there, and yeah, just carbon to fluorine. So we're only thinking about 4 elements here. So we're thinking of carbon, nitrogen, oxygen and fluorine. Now, knowing the trend in atomic radius across periods 2 and 3 is going to be important. The trend is that the atoms actually get smaller as we go across the period, and that might seem a little bit weird to some of you. I know I found this initially quite weird way back when I was doing my A-level, because when we go from carbon to nitrogen to oxygen to fluorine, we're adding an extra proton into the nucleus every time, and therefore we're adding an extra electron to that outer electron shell. So I was thinking, how can the atoms possibly get smaller if we're adding extra subatomic particles in? But it's the addition of those extra protons that means that the electrons get attracted more tightly towards the nucleus. Because yes, we might have an extra electron being added as well, but because the shielding is the same or similar, the electrons are going into the same main energy level because all of these elements are in the same period. So because we have an increase in nuclear charge, or an increase in the charge of the nucleus, or an increase in the number of protons one of those three ways of saying that, and the shielding stays the same, that means the electrons will be pulled in towards the nucleus most tightly in fluorine out of these four examples, and carbon would be the biggest atom of those four, because with fewer protons, the protons in carbon's nucleus less able to attract the electrons as strongly. And that's why it's really important that we always check which elements we're considering, because if we were thinking about the largest atomic radius across the whole period, we'd be thinking about lithium, but we're only going from carbon to fluorine, and they've done that purposefully to check whether people are reading the question. So how am I going to put that into words? So we're going to identify the period 2 element, so that comes first. So carbon, because there is an increase in nuclear charge across the period, whilst shielding stays the same. You can say, oh, the shielding is similar. Either is fine, and that's because the electrons are all going into the same main energy level. Therefore, the electrons in an atom of carbon are less strongly attracted by the protons in the nucleus. Hopefully that makes sense, but as always, if anybody's got any questions about any of these answers, please leave a comment on the video or drop me an email to missgtutoringandresources@outlook.com. Okay, so that's the first question. Second question, again, bit of a longer answer question here. We've got to do some explaining. So first of all, we have to state the general trend in first ionization energies from carbon to neon. So we're adding neon on as an extra element this time. So that's the first thing we have to do. Then we have to deduce the element that deviates from this trend, so find the anomaly, and then we have to explain why this particular element will deviate from the trend. So the two anomalies, as I said at the start of this video, are when we jump from the element in group 2 to the element in group 3, and that will either be beryllium to boron or magnesium to aluminium. If we're only looking at the elements from carbon to neon, it can't be that anomaly that we're considering, so it's going to have to be the second anomaly, which occurs between the elements in group 5 and group 6. So for period 2, it's going to be that there's a dip from nitrogen down to oxygen, and if the general trend is that the first ionization energies are increasing across the period, we're looking for the deviation where we see a drop rather than an increase, and the drop will be oxygen. So oxygen is therefore the element that deviates from the trend, and I'll explain why that is in a second. For the general trend, the first ionization energies will increase across a period. Now there's 5 things that we should be thinking about when the question is asking us about first ionization energies. We need to be thinking about the charge on the nucleus, distance of the outer electron from the nucleus, shielding, repulsion, and energy of the sublevel. Now, the first 3 are used to describe trends across a period generally, or to explain the trends down a group. The last 2, the repulsion and the energy of the sublevel, are used to describe and explain what's going on with those deviations from the trend. So when we think about it generally increasing across a period, it's very closely linked to the atomic radius argument, As we go across a period, the number of protons in the nucleus will increase and the shielding stays the same. And that means that the atomic radius gets smaller as we go across the period, as we've just talked about. And if we're thinking about first ionization energy, which is removing one electron from an atom to make a singly positive ion, that will be harder to do with an atom that's smaller, because if we're coming in and trying to take an electron away, the more tightly held that electron is, the more energy we have to put in to overcome that attraction. If the electron's not held as tightly, then we have to put less energy in to take the electron away. And the first ionization energy is a measure of the amount of energy it takes to remove that electron from the atom. So the general trend is that the first ionization energies increase. The reason why we get a decrease in oxygen is linked with how the electrons are arranged in those p orbitals. So the p sublevel is made up of 3 p orbitals, and one of the rules that we need to know about how these orbitals are filled, which is Hundrel, he said that the electrons will singly occupy those p orbitals before they pair up. So an orbital can hold 2 electrons, but rather than one orbital having 1 electron, then getting a second, then the next orbital getting 1 and then a second, and so on. It doesn't work like that. We actually put 1 electron singly into each of the 3 orbitals first, then we go back and start to pair them up. And the analogy that my teacher used with me for my A level, that I still use today, is that if you're getting onto a bus and you don't know anybody on the bus, you probably wouldn't choose to sit next to a stranger if you could sit on a free sort of double seat. So that's how I've always remembered it. I used to get a bus to school, so it definitely resonated with me. And that's what's going on here. So the first electron will go into its own orbital, the second p electron will go into a separate one, and then the third p electron will go into the third orbital, so they'll all be singly occupied first. When we get to oxygen, we then have a 4th electron. We don't have any more orbitals, so that 4th electron has to pair up with one of the electrons that's already in one of those p orbitals. And if you've got 2 electrons that have the same negative charge occupying quite a small space, they are going to repel each other. And if they're already repelling each other because they don't want to be that close together, it makes it easier for us to come in and remove one because they're already fighting with each other, not wanting to be in that same space. So it's actually quite happy well, not quite happy, but happier for me to come in and take that electron away. And that's why we get the deviation there. So in terms of how I'm going to explain that, first of all, state the general trend. So general trend increases. So an increase in first ionization energies. So that's going to be one of these 4 marks. Second mark is going to be for deducing the element that deviates from the trend. So oxygen deviates from this trend. And then we've got to explain why. So when we're explaining why with regards to this particular anomaly, it's really important that we talk about the specific sublevel and orbitals that we're talking about. So rather than just saying there's a pair of electrons in an orbital, we should say that oxygen has a pair of electrons in a 2p orbital, and it's the p part of that that's the most important, and that'll be underlined on the mark scheme in most cases, if not all cases. So that's the first thing I'm going to say, that oxygen has a pair of electrons in one of its 2p orbitals. The second mark for this explanation is going to come from saying that there will be repulsion between these electrons. And it's usually just the word repulsion that they're looking for, to be honest. We don't need to write reams and reams for this answer, which is nice. So repulsion between these electrons makes it easier to remove one of them. And if it's easier to remove one of them, then we're going to have to put less energy in to do that. Okay, so it's really important that we specify which orbital here that we're talking about, and no harm in also saying that it's the 2p orbital. If we were thinking about phosphorus and sulfur, you'd have a pair of electrons in one of sulfur's 3p orbitals, and that sort of reference to the specific orbital is important. Okay, don't need the periodic table for now. Next question says that we have to write an equation including state symbols. Very handy of them to remind us of that, because they won't always necessarily, particularly when you get to some of the year 13 content, but in this sort of year 12 scenario they tend to tell you that state symbols are needed. You will always need them in any first ionization energy equation, and we're doing it for the first ionization energy of carbon. So essentially what we've got to do is show what's happening when we take an electron from carbon as an atom. So you've got to understand obviously what first ionization energy is referring to. We always start with the atoms, and they will always be in the gas phase, and that's unusual for us to be thinking about carbon specifically as a gas. But for the elements that are not gases, the first thing that we would need to do is vaporize them before we ionize them. It'll always be gaseous state symbols here. And if we are then removing an electron from an atom, we are going to make a positive ion, which will also be in the gas phase, and then obviously we will have the electron that we have removed from the atom on that side as well. Now again, you don't see carbon as ions. Carbon doesn't undergo ionic bonding. Carbon will be sharing electrons to form covalent bonds, but we can, for any atom, for any element, take away all of its electrons in turn, which we would call those successive ionization energy. So this is the first. There'd then be nothing to stop us from taking away a second and a third and a fourth and a fifth and a sixth, up until, you know, you've got no electrons left. So always gas state symbols, always atom to unipositive ion plus electron for the first ionization energy of our element. The next question is then thinking a little bit more about those successive ionization energies. So we're comparing the second ionization energy of carbon to the first ionization energy of carbon, and we have to say why the second ionization energy is higher, i.e. why it takes more energy to take that second electron away. Now if we're comparing this for the same element, which we're dealing with carbon, what I like to do is write down how many protons and electrons that we're thinking about. So for carbon, we have got an atomic number of 6. So we've got 6 protons and 6 electrons in our atom of carbon. When we then do the first ionization energy, we're taking the first electron away, and then we will have still 6 protons, because we're not changing the number of protons here, but we'll now only have 5 electrons. When it then comes to the second ionization energy, we're going to take another electron, a second electron away, meaning that we would then have left behind 6 protons and 4 electrons. And every time we remove an electron, obviously the number of electrons will decrease by 1 each time, but the protons is going to stay the same. And that's what's really important. When we're trying to take the first one away, we have 6 protons attracting 6 electrons. So essentially, one way of considering it is that each proton has its own electron that it's sort of responsible for. Once that first electron has been removed and we only then have 5 left, the 6 protons each can still be responsible for one, but then there'd be one spare proton, which can help in attracting those remaining 5 more tightly. So every time you take an electron away, the 6 protons that remain will be able to more strongly attract the fewer electrons that are left. And that would be the case every single time. So if we were to see a graph of sort of successive ionization energies, they would increase for every electron you removed, because of the increased attraction between the protons and the nucleus. So that's what I need to write here for my 1 mark. So there is an increased, that's a weird way of saying that, I probably should have just said stronger, but I'll put increased strength of attraction between the protons and the remaining 5 electrons. Which will make it harder to remove the second electron. And it would then be harder to remove the third than it was to remove the second, because we then have 6 protons only attracting 4 electrons. Then it would be 6 protons attracting 3, 6 protons attracting 2, 6 protons attracting 1. So that last one is going to be particularly difficult to remove. Okay. And then finally for this question, we have to deduce the element in period 2, and we're now considering the whole of period 2 from lithium to neon that has the highest second ionization energy. And questions like this cause people to panic sometimes a little bit, or to feel like they don't have the knowledge to be able to answer this question, because there is a huge focus on first ionization energies and not really second. And if we were thinking about the element in period 2 with the highest first ionization energy, that would be neon, because as we go across the period, first ionization energies increase. Neon is a noble gas. Neon has a full 2p subshell, has a full second main energy level. It's not really going to want to give up an electron. We know that noble gases are not very reactive for that reason. They are inert. So some students therefore think that removing a second electron from neon will then also be the hardest one, based on that information about the first ionization energies. But what we need to consider is where that second electron is going to be removed from. So if we remove 1 electron from neon, it will then be 2p5 for the electrons in the outer p sublevel. So we'd still then be removing an electron from the p sublevel, and that would apply for fluorine and oxygen and nitrogen and carbon as well. Boron, once you've removed the first electron from the 2p sublevel, that would be 2p1, get rid of that electron, we'd then be removing it from the 2s. So still in the same main energy level, but we are in a sublevel that's closer to the nucleus. So that would take slightly more energy. But the big one is when we're then thinking about lithium, because lithium's configuration will be 1s2, 2s1. If we then remove that s electron, the 2s electron, we would then have only 1 main energy level, and we'd go down to 1s2. So if we were then wanting to remove a second electron from lithium, we'd be removing it from the 1s orbital, which is in a whole main energy level closer to the nucleus. And that's what we're watching out for also when we think about successive ionization energies. They will always increase stepwise, but you might see a big jump when you get to a change in the main energy level. So that's what we're looking for here with our second ionization energies. So it will be lithium. And again, it just says deduce the element. So name or symbol would be fine. So the answer here is lithium. We haven't had to explain that because we're only getting 1 mark here. But for the benefit of you guys and this video, I will explain it in brackets. So it is lithium because the second electron would be removed from an energy level closer to the nucleus. And if we're removing it from a main energy level that's closer to the nucleus, the protons are going to be attracting it more because the distance has changed. So again, thinking about a very crude, here's my nucleus, here's my first main energy level, here's my second main energy level, here's my third, and so on and so forth. If we're moving from the second to remove lithium's first electron to the first main energy level to remove its second electron, the distance between the nucleus and that electron has decreased. There's less shielding as well, because when we removed the first electron, there was the shielding from the 1s2 electrons. When we get to the first main energy level, no shielding. So with the decreased distance and less shielding, the protons in my nucleus will be attracting the 1s2 electrons more strongly, making them harder to remove. Okay, so those are my answers for that question. As I've said, any questions, please do not hesitate to ask me. This can be a little bit mind-boggling because it feels very abstract. Obviously, we can't see these atoms to be able to, I guess, validate this sort of thinking. So if there are any questions at all, please let me know, as always, and I thank you so much for watching.